second one. For the second one is the wireless RF basics. So how this RF works? RF, the radio frequency. How this radio frequency works? What's the parameters we use to like analyze, to measure this signal, right? So electromagnetic waves transmission. This is the wireless, right? We use these waves to carry the data we want to send from one transmit devices. From the AP, for example, we generate the data and we do the modulation, and this data be carried by a you can say, we could call it the electromagnetic waves. It's be carried by these waves and through the air. Lots of times it's through the airs because it's hard to penetrate the waters. It's hard. So we use this wireless to carry our data go to another devices, for example, phones, laptop. After it's received, it also have to use the wireless adapter, right? We can follow the IE standards. We do the demodulations. After the demodulations, this data can be received. We can receive the message hello, right, from our friends or from our families. So how we can understand how these electronic waves transit in the air? First is like we have antenna, whether it's building antenna or the external antennas. We have this one. We have this antenna and the signal going to the antenna. There's the electrode, and the electrode, when the electrode moves, we have the magnet, right? Because this is two fields. It's just like a combination of electric and magnetic field. With these two, one generation, the electric generated magnetic and magnetic generated electric. These two work together and generated the waves. So the wave is kind of energy that transferred to the for other place. So this is the electromagnetic waves. So one way to help to understand, you consider is like a voice, right? So we speak, it passes into the airs, and when transfer longer, it's become the weaker. When we near the voice is longer. So when the wireless signal transmitted during the airs, it have the penetration loss. So for this space propagation loss, we can have different categories. First, like absorption, is when you penetrate the wall, right? The energy be absorbed by the walls or the losses. Yeah, after it's reflection. Reflection is just like when you're going to a mirror, right? This be the direction of the signal be changed. Before they want to go to the CR, right? And when they see a mirror, and this one, the mirror changes this direction to another place. Also the scanters. The scanters is like the dust in the air. When there's lots of the dust in the air and our signal penetrate these airs, actually the dust change the signals direction into the different place. And then is the refraction. Refraction is like the signal going to from the one, for example, from air to the water, right? This direction also change. Is another way for the signal's direction to be changed. We call it the refraction. Also, even this wireless penetrate in the free space. Actually, that means that no any other obstacles. The pure air. no other obstacles, this energy still will be lost because these signals continue to actuate even if no any obstacles. So this one is very important. Here's a free space path loss calculation. Uh, this this formula is like a little bit mess on the mess side, but it's easy to understand. The idea we want to know from this volume is first one is that this free space path loss is relative with the frequency we're using and also the distance the signal transfer. For example, we are using the 2.4G and the transfer after 100 meters transmission. How many dB will be lost, right? We can remember this one for our Wi-Fi like experience. For example, there's the one signal, right? This the transmit signal is the 20 Mbps. So logically, if the signal transmitted by 100 meters, it should have 8 8 8 dB 80 dB loss. So the signal will become a minus or negative negative 60 dB, right? And also, if the signal be transferred for 200 meters, the signal should be how much? Or like the negative 66, almost like near the negative 70 dBs, 70 dBs. So here is from this formula we can see one rule for us to calculate this signals transmission distance. We call it the 6 dB rules. This one is if we are doubling the transmission distance, if this signal be increased by the 6 dB, it's just like before you have one AP. This AP's transmit power is the 20 dBm. So 20 dBm after it transferred 100 meters, 6 dB, right? So this is good for use. Right now you have a client in the 200 in the 205 away from you. So you need to change this AP to a bigger transmit power. You chose the AP. We have the transmit power is 26 dBm. So use this AP, the signal can reach the 200 far away 200 meters away place. So the device is there when you receive the signal. It also 60 dB. Negative 6 dB, so it's good for Wi-Fi use. So for the penetration loss, for the different loss, first one is absorption. Absorptions. So absorptions is the mainly reason that for our signal become weak when we do the project, right? When we do the site survey, there may be a war, maybe there has the glasses, the obstacle doors. So we need to consider about these things when we do the project. So this is the penetration loss estimation for the different materials. The highest one is metal. So this one is, for example, when you go to the elevator, definitely there's no signals for the Wi-Fi. Also no signals for your mobile phone signal. Mobile signals like the LTE, right? So this is the same because the metal can almost block all the electromagnetic magnetic waves. So when we do the project, just if that wire or sail is metal, just put that AP in front of the mantle or don't put it behind the mantle. If you do that, the signal will be very bad. And another is like when we see the upgrades like the wood and yeah, for the especially wood, when we do the project, if we find that they have different room, but this room is be separated by the wooden board or other like glass things or other actually glycation is a little bit sometimes it depends because some glass is very thin. Some glasses if you use another materials. The glass is hard to think. Other like the cedar blocks, this kind of the materials. Actually, we can use the 1 AP the coverage 2 or 3 rooms, because our signal can easily penetrate that material. Also, the refraction loss. So we have this signal from one direction change to the another one. So this reflection and also this kind of the phenomenon of the wireless signals, the cost multipass, because 1 AP, right? We have the 1 AP. The AP have the signal. When this signal go to our phones, maybe the signals go to the different way at the same time, because it be changed maybe. So when our laptop terminals receive, maybe they receive multiple signals from the different direction. So before, if our devices do not support MIMO, so they don't know how to handle this kind of situation. So that means sometimes even that your phone is have very good signals, like the 4 bars here that we think, right? 4 bars, but this user experience is very bad, and the internet speed is slow. Maybe because of this reason, but that just mean that your phone do not support the MIMOs. But if your phones also support MIMOs, it can utilize this kind of these multiple waves. And then it's a reflection loss. For the reflection loss, usually we have the effect on our outdoor project. For our outdoor project, if we do the point-to-point wireless bridge, sometimes our customer will be maybe have a complaint, right? When they have the rainy or they have these storms, these the signals, the leak become weak, the connection lost for some times. So this is because of the refractions. Because when the signal, we were using the 2 devices side of light, they face to face, they see each other. But because of the airs or dust in between these 2 devices, the signals change their direction. So that is another thing we need to consider when we do this wireless project. And then a third part is the RF's characteristics and parameters, like just what's the measures, how we can value these signal strengths like this. First, let's see the RF, these kind of these components. What the components is used for these wireless products. So how we can generate a wireless? First, we have the transmitter. For the transmitter, we have the feeders. After the feeders, we have a attention radiator. We have the intentional radiator. Intentional radiator. Where's the intentional radiator? Intentional radiator is the point at which antenna is connected. So you just be careful. This point is not the point on the AP. It's not the connector on the AP. It is the point which connects the antenna. Right? That's me. This included the feeder. This after the feeder. The feeder connected to the AP, and our antenna connected the antenna. Our antenna connected its feeder. So the point, the antenna connected, we call it intentional radiator. So the signal generated and the transmitter and may pass through the connectors, amplifiers, actuators, and cables. We hear cable called feeders before reach the antenna. So this is the radiator. So the signal after the antenna, after the gain, we call it is the equivalent is tropically radiated power. Okay, if you are newcomers, please mute your microphone. Thank you. And so this is the EIRP. And here we need to know the difference between the IR and the EIRP. That's me. That's me. Even we don't have antenna, right? Even we don't have antenna, we still have signal, but the signal is wrong. But the signal is not that wrong. It's from the intentional radiator or the transmitter. We still have the signal. The signal is not strong. So if we want to be stronger, we add the antenna. After the antenna, the signal become the EIRP. EIRP. Why we not notice this kind of term? Because when you check some documents, maybe some introduction of products, they will use this kind of terms. So better to know these kind of terms when we do the wireless project. Okay, here is the units of the power that are measured in the RF system. We usually use it like milliwatts, MW. The symbol is MW. So that is the milliwatts. So this one is, for example, our indoor AP, the signal is 100 M watts. It's okay, we can use this M watts. The transmit signal is 100 M watts, milliwatts. Yeah, so they have the like the 10 milliwatts is the 10,000 10 watts the equal 10,000 milliwatts. That is a formula. And also we have used the dBm. So here maybe you are confused why we use the dBm. For the dBm, because when we see that when the power become very big, for example 10,000 10,000 or 100,000 milliwatts, you need to use the one and the multiple zeros. So this is hard to present the larger or very small the power, because sometimes we use a negative. Sometimes we have the signal like the 0.00001 milliwatts. If you use this milliwatts, it's hard for the writing or the expression. We also the people use the dBm. For dBm, use the 10 log and log, and then you use the power in the M watts. So here example for we calculate, you will understand that the 100 milliwatts equals 10 log and 10 divide 1. For this one is that it's like the result is the 10 plus the 10 plus 2. This that equals 20 dBm. And also after the dBm is the dB. We know that dBm is absolute value. It's transferred from this milliwatts, right? It's transferred from milliwatts. But when we use the dB, actually is the relative. It's a relative value. It's a relative value. That's we usually we say that this signal is increased by 3 dB, 7 dB, 9 dB. We don't use the dBm. Remember, just there's the difference. When we say that the signal is increased by the 7 dB, 6 dB, we use the dB. We don't use the dBm. So here's the difference. And the last one is the dBi. The dBi to use the present the antennas gain. You can think that it just uses a different scenario for our using, for our daily usage. Just have this kind of understanding is okay. But yeah, they don't have the big difference between the dBm, dB, dBi, but they're using the different scenarios. Okay, go to the next page. So here's the basic RF mesh for how we can calculate or the transfer from this dB to dBi like this. This one 6 dB rule we need to remember, and also have another 3 dB rule. 3 dB rule, like the gain per 3 dB double the absolutely power. For example, it is 20 dB, right? 20 dB, that is 100 milliwatts. And if your transient power is 23 dB, the transient power will be 200 milliwatts. So you can think that's the difference. So these are 3 dB rules. We have 6 dB rules, 3 dB rules, and also we have 10 dB rules. For 10 dB rules, that's every 10 dB loss of value, absolute power will be divided by the 10. For example, you use the 10 dB. For the 10 dB, what is the value? That is the 0 0.0 milliwatts. And a negative 10 dBm. This equals the negative. This equals 0 0.1 milliwatts. But if the signals change to a negative 20 dBm, the signal will become 0 0.0 milliwatts. You can see the signal is be lost by the 10 times. So this is the 10 dB rules. So this 3 dB, 6 dB, and 10 dB rule can help us to, if you're not, to help us to calculate the dB m from the milliwatts very fast. But if you want just to use the law and that formula, it's not convenient because usually we don't remember the, we need to use the calculator for that one mostly. Here's another, next is another technical terms we use in the RF. First one is a signal to noise ratio. We also call it SNR. For this SNR, lots of the devices, even in our APs or controllers, we show the SNR. We also sometimes we show the noise floor. So what it does mean? It means that you have a signal from your device and your phone will receive this signal. For example, your signal is when I receive, the signal is the negative 60 dBm. So here you can see when we say signal with a dBm, we're not using the dB. So when I receive this, the negative 16 dBm. But the noise, this environment, there has a wireless noise. The noise is, for example, the noise is 100, negative 100 dB. So for this situation, my SNR is 20 dB. For a wireless project, if the SNR is 20 dB, it's pretty, it's already good. It's already good. So if the SNR, for example, is lower than the 50 dB, this is too low. So if this SNR is too low, that's mean that your signal is mixed with the noise, right? When your device is receiving noise, you cannot identify the noise and the signal very clearly because they mix together. They're just running in the same level. You don't know which is the signal, which is the noise. So the signal to noise ratio, we call it SNR. For this one, the recommended value is 25. 25 or above is definitely a good signal quality. Here he give you an example. Give you an example. Just they give us an example that usually when we do a wireless project, we usually ask the we usually like receive the signal is the signal strength is the negative 85. Negative 85. This signal is our phones can identify. This signal is like lots of the phones. If the signals is lower than the negative 85 dBm, it cannot identify. It's like lost connection, very bad speed. So we need the noise floor at least to be like smaller than the 100s, lower than the negative 100s. So sometimes if your if your environment is have the interference, so make sure that your signals is strong. It's just like the balance. If the noise floor is high, just make sure that your signal stress is higher. It have the difference, a bigger difference between these two signals. Next one is RSSI, that's receive signal stress indicators. This one actually we see this one every day. So this one is like, for example, when we think our phones, we say that how many bar is the signal stress. We call it the 3 bars, around 75%, or sometimes phones shows that it's in the like 90% signal stress. So this one is RSSI for that devices. This one, we need to pay attention to that. For this RSSI, it is a standard. It is a standard. Defined by the 802, i.e. 802.11. It also provides a range from 0 to 25, but it is the arbitrary measurement. Arbitrary measurement. That's me. This organization didn't give the specified the definition for these indicators. For example, the rates. So the vendors can choose their own. So this have a result like maybe when you use the Apple, you see the signal is a 4 bar. Then you use the Huawei, and Huawei's phone is not the 4 bar, just like 80%. This is happens. So it's just because they are using the different RSSI in their devices. This table is show one devices. I'm not sure this device is from each vendor, but it just show you that for these devices, it RSSI, the max RSI is the 13. That's mean when these devices detect the signal stress is negative 30 dBm, it will show the signal stress is 4 bar, 100%. But if the signal stress is like weaker than the negative 75 dBm, the signal stress is show the only 40% in that bar, in the signals bar. Okay, this is the RSSI. Next one is a Wlan signal propagation mode. So here we need to analyze this mode, and we calculate, later we'll calculate the loss during the transmission. For this, the power is received by our devices. It is the power of this, the gain part, like the transmit power and the gain from the antenna, and minus the pass loss, and also plus the gains from the receiver's antenna. Because we know that when the signal is transmitted, it will amplify. It will be increased in the transmit antenna. After received, it also will be increased by the received antenna. So here we go into the leak budget. For this leak budget, we need to know how to calculate. For the why we calculate leak budget is usually used in the outdoor project. For example, we have outdoor project. We have 2 places And we know that this AP's transmit power, and we know that the gain of this antenna, and we know the distance of these two APs. After this, we want to we want to know in advance what we want to evaluate. We want to evaluate uh, the signal stress, if that is the signal stress will enough for this transmission, for this wireless bridge. So in this destination, we need to calculate the leak budget. For leak budget, one thing is the first one is the free space loss, right? Because the space, the signal transferred in the areas will have a loss. And also another is the insert loss. Insert loss is like when you connect, we connect a feeder, right? In that connectors between the AP and the feeder, you have the connector. The connector maybe cause a loss. The signal maybe feel not comfortable at that point. So the signal may be increased by the 0.5 dB. That's what we call insert loss. Here is a case that together we think that how this signal, how is this leak budget works. So you can see that for the transceivers, it have the feeders. The transceivers have the 10 dBms increase, and then when they go into these feeders, the feeders miners, and also the lightning arrestor, they have a lightning arrestor for the antenna. So it's also decreased for their 1 dB. And also for this antenna, this is the parabolic antenna. So it's the equal 25 dB, the same. This other side, with the receive the increase antenna, and then so for the calculation here, the table. So what the signal it will be, what the signal stress when the receiver receive the signal. This is the signal. Receiver signal is the negative 65. Negative 65. This is the logically the signal stress that the receiver AP will get. That's the negative 65 dB. So for the assuming that the receiver sensitivity threshold of this receiver is the negative 80 dBm. That's the because we receive the signal, we will receive a signal that's the negative 65 dB. So let's say we have 50 dB for its buffers, right? That's me. This signal maybe there's rainy. It can be lower, the weaker, like that. When they arrive, it become the negative 70, negative 75 dB. It still can be received. So this we call it the fade margin. So the fade margin is like larger the fade margin, the better for our wireless project, right? So it's recommended to use a 5 dB fade margin at least in our wireless project. This is also why we suggest. That is also why we suggest to use the 57 dB in our Wi-Fi project. Some people, we do this kind of project, but we don't know why we need to use the negative 65 dB. Here's the reason. For our phones and the AP to have a speed 55 Mbps, 55 Mbps. This is very low speed already. For our devices to have this speed, we need to have negative 70 dB. So negative 70 dB, this is a signal. This is a signal stress. We can achieve 55 Mbps between the device and the AP. So also we need to consider another 5 dB fading margin. There's maybe people around. Maybe you have a devices, you have a phone, you're walking, and some people walk before you. It's also blocks. So you have that 5 dB fade margins. So the signal stress coverage for our office, like for our like the candy room, uh, classroom, it must be above, at least should be negative 65 dBm. So when we have this negative 6 dBm, that's me, at least it can have 55 Mbps. Some people will be like, well, what will happen if the signal go to the -7? Actually, -7 is okay. It's the speed is not that high, right? Because we know that our speed for the Wi-Fi speed it can be 11 Mbps, so just speed will be lower. And when there's another interference, maybe they have uh, very bad experience. So that will happen. So recommend the coverage signal is negative 65